I'm recording now, and I'm about to share my screen. All right, can you guys see my screen here with Canvas? And I think I have Keynote up here, PowerPoint.
Yep.
Okay, great. So welcome. The recording will start here in just a second. All right, welcome. I'm going to go ahead and just play this. In the syllabus, we mentioned that, there are serious folks doing serious things with these tools. So I thought we would just go into a couple of examples that some buddies of mine out in the real world give me and let me sort of show to you guys. And so the first one is dealing with the building envelope, or the skin of the building, right? The facade. So if you look at the elevation of this thing, it looks sort of light and glassy, right? This is a research building on a campus in Australia. So it's in Adelaide, Australia. And there's laboratories and all sorts of things in this building. But I thought I would sort of quickly run through some of the process that they shared with me. And so first of all, when it comes to this sort of form, you can see the shape is not a typical sort of shape, right? So one of the things that they're dealing with is this sort of odd shaped site that they were dealing with, where you have several roads coming in and they're not at 90-degree angles. So you have a sort of rotated grid, which sort of gives you a diamond or chevron shape, or sort of American football, but with points starting off with. Then they start to round things out. And so you can start to see the sort of logic of how they're starting to rationalize the form. In fact, this is what it's called, right? So this diagram, right? And so trying to sort of figure out how to fit the sort of constraints of the site and the constraints of the program and square footages and things like that, and building a geometric logic to how to sort of, turn a corner or fillet a sort of large or sharp corner, things like that, right? How to bevel these tops and everything else. And I think you'll start to see that what they're doing here is they're starting to build up again, a sort of conceptual logic for, how they start and how they made decisions in a rational way. And in turn, they use this to sort of, again, to communicate to a client, but then also to communicate to everyone else downstream, right? And so they get this shape or the form, then it's about taking the facade, right? Or the skin, the envelope, and starting to make sense out of it, right? So you can see that there's a bunch of geometry that isn't standard, right? Some of it's planar, some of it's curved, some of it's doubly curved, right? That becomes really difficult to make. And so beginning to rationalize, again, a complex, large complex form into a set of componentry. And a lot of architecture is about this, right? You can make a model or draw or sketch something very quickly, but ultimately those are kind of like dumb surfaces and big expanses of walls or a long span of a roof or something like that. Turning that into architecture, into a set of pieces and parts that can be fabricated and then assembled and put together in that perform in a particular way. Maybe it's structurally, maybe it's thermally, or maybe it's regarding shade and light, and also aesthetically, right? When it comes to balance and proportion and density and scale and those sorts of things, right? And sort of, negotiating all of these sort of competing constraints, right? That's what this thing of this beautiful process of making architecture is really all about, right? And so these tools, I think, is one way to sort of help you in doing that, right? Taking a large idea and then beginning to sort of turn it out and actually gaining more control over the process, right? Of how things are made and how things go together on site, right? In the field, right? And so basically it's taking a large shape and breaking it down into several regions, each one with their own sort of constraints and inherent challenges and the like, right? I'm just gonna go ahead and, not sure, I'm gonna go ahead and hide that thumbnail video. Okay, so, and so you can see, right, each of these sort of four directions where they can get these sort of planar patches, they're gonna do that, right? So these blue parts are nice and planar pieces. They have parts that are at the top, parts at the bottom, parts that turn the corner, right? This corner versus that corner versus this corner versus that corner. And then there's even an underbelly, right? Where you can start to see some violet and some green and things like that. I'm trying to develop a logic for how to take these large shapes and break them up into components. And what you'll find is that it's easiest, in this case, it would seem to be easiest to sort of break them up into triangles, right? So in other words, what's interesting about that is a triangle is always going to be planar, right? So 3 points, you can always draw a plane through 3 points. And so taking something that looks doubly curved and then approximating it with a set of planar triangles in this case. And so that was an initial decision that then, you know, they made and stuck with in order to sort of rationalize this sort of really difficult geometry into something that could be fabricated and assembled under or with a budget, I guess you might say, right? And so here it is, right? This is a firm, Woods Bagot. It's an international firm. They have offices all over the place, and you can see that they're taking parts of these surface patches, breaking them up into rectangles, and then diagonally slicing each rectangle into a triangle. Right? At the same time, sort of looking at each of these, you know, trying to sort of understand the performance needs, right? So once you start to place this in the sun, right? In this case, this is in the southern hemisphere, so the sun is on the north side of it. Yeah, you can begin to see that as you move around this building, right? The south side has different constraints and different solar loads and things like that than the north side, and the east versus the west. Right. And so as you move around this, right, you could actually begin to sort of understand how much daylight you need based off of the program behind the facade, right, on the inside. But you can also begin to map the amount of solar radiation that hits this in any given day or any time of the year, or even an average over the entire year. And then taking those energy values and beginning to, right, you can see here that, you know, quite a bit of this facade gets a lot of sun, right? But then parts of it are underneath are sort of self-shading, and so they can be more open, right? They don't have to worry about shading from direct light. Right? At the same time, they sort of developed a logic for the sort of shading devices that would be deployed along the envelope, right? And again, what I would call this is sort of a, you know, it's sort of a this idea that, you know, you can have this sort of genotype, but then you can generate any number of phenotypes based off of just changing a few parameters, right? You change it just a little bit of that of those genes, right? And then you get it like a, you know, a different organism, right? So here, you know, you can see that the shading devices could be much deeper, right? Or they could be very shallow. Right? They could almost close things off, or they can sort of move upwards, right? And so this point, right, this sort of three-sided pyramid can move around, and then also can become deeper, stand off further from the facade, or get much closer to the facade. And what that does is that allows you to sort of fine-tune each of these panels, right, for how much view you can let out, how much privacy you need from outside in, and then how much shading you need from the sun up above. Right? And so you can see that there's all kinds of different variations they can begin to do from this very simple recipe. Right? And then here's a Grasshopper model of part of that facade. You can see part of that facade where you're turning a corner. So you can see there's a top, a center, and a bottom, and then even wraps underneath, reaches around, right? So each of these are broken up into triangles. Then you can start to map the data onto it, right? You can see that each of these gets deeper or shallower, and also the points move around. You can even color code them or sort of visually understand where there's more closed and more open cells. Right. And then flattening each of these out, I think, is interesting, right? So each of these pieces, when flattened out, then becomes a sort of both vector information you can send right on to the fabricator, make sure the shop drawings work out all right, and then they can, you know, they could use CNC equipment to cut each of these out. What's interesting is that each of these cells, each of these panels is completely different, right? Sometimes only by millimeters, right? And so each one is labeled in a particular way, right? So that you can put the jigsaw puzzle back together in the shop or on site, right? Further on down, right, the sort of steel folks and the curtain wall folks take this take the information from the Grasshopper file, and then they use it in their own software in order to make this sort of fabrication drawings and the shop drawings, right? So you can start to see a level of detailing here that the architects and typically the engineers don't even do, but that the fabricators do, and then the engineers double check. When you're doing a custom curtain wall, they actually mock these things up at full scale. And then it's really interesting. I don't know if you've ever seen this or not. If you haven't, get onto YouTube sometime in your free time and look up curtain wall testing. What they do is they get a jet engine, and what they do is they blow incredible winds, lateral loads at this thing, while also throwing water at it, right? And trying to sort of make sure that structurally it's going to withstand wind loads of a certain strength, and also that it's sealed and it's not going to let moisture in. So it's a pretty incredible process. But what you can see here is that you take a large shape, you break it up into smaller zones. You take each of those and break them up into panels. Each of those panels are comprised of these components, right? And so if you think about all these custom components, it's a lot easier to put a lot of them together in a factory setting, right? And then eventually, right, these panels are then brought to site and they're clipped on, right? Just like you would with any other kind of curtain wall, right? So you can begin to see, at the same time, simultaneously, or in parallel with making the curtain wall, they were pouring the frame, getting those slabs in. You can see, there's all these clips and things like that to sort of hang the facade onto, and that's modern day construction these days mostly, right? So in this case, it wouldn't make sense to get thousands or even millions of pieces that are all different on site. So what they did is they said, well, what are we going to prefabricate in the factory, and then how can we again speed things up then on site where you have the sun and heat and wind and dirt and grime and everything else. So you can begin to see this sort of cheese grater like facade, and you can begin to see, right, how it turns into also the branding of the building, right? So certain portions of the building actually begin to glow at certain times, right? And so views in and out of the building are governed parametrically, right? Differentiated across a sort of field of these similar yet slightly different or serially changing facade components. Right, and so you can see at the pedestrian level, it becomes downright, they almost disappear, right? They become, well, they do disappear at the very end, right? They start to sort of push back until they disappear and become so thin you don't even see them, to sort of open up at the pedestrian level and where you have shading anyway, right? And so again, this isn't the idea that rather than sort of saying one size fits all approach, I'm going to make one shading component that can be repeated all over the place, right? It's an acknowledgement that, maybe the south side and the north side and the east side and the west sides of the buildings and the tops versus the bottoms can all use the same sort of geometry, sort of vocabulary, but at the same time, they're all sort of different, right? And so if you can negotiate, let's say, shading requirements, daylighting requirements, the program on the inside, the environmental forces on the outside, then you have, I think, a really sort of smart building envelope, right? And that's the key thing, right? The value proposition here is A, something iconic, and B, something that works really well to save you on your utility bills. Okay. All right, and so you can see again this sort of workflow. There's no one tool that did all this stuff for them. They were doing the non-standard modeling in Rhino, bringing it into Revit, right? Then when they needed to take the sort of rationalized zones out and break them up into small pieces back into Grasshopper, then they wrote their own Rhino script, right? In order to sort of take the data from here and bring it into Excel, right? At the same time, they take the geometry back into here and back into Ecotech to do the analysis with the sun, taking that data and using Visual Basic to bring it into and plug it into the Grasshopper file again, and on and on and on, and then back into Excel, back into Visual Studio, back into Revit, in order to sort of turn it and make it into take the BIM model and start to make drawings from it, right? So again, it's really this sort of fluency, right? How to take information from one platform to the next without losing the critical information or the fidelity of the information. And so again, this is very much going under the hood, but when you're doing sophisticated things and pushing the boundaries technologically, right, which I hope we, as architects, we start to do more and more of, right? It requires getting under the hood and not just being consumers of the software, but really sort of understanding how the information works and even customizing the software a bit here and there, writing some scripts or making a graph in Grasshopper or making your own smart object in Revit or your own family of objects in Revit, etc. Okay. All right, here's another example that's actually closer to home. So the previous example, that'll, I think, really come into focus a little more when we do project 2 and we're really working with surfaces, breaking them up into smaller pieces and talking about developing shading components and things like that, right? This one deals much more with trusses. The firm Populous, this was a sort of multi-program, sort of multi-use facility that they did as an add-on to the football stadium in Jacksonville, Florida. So this would be part practice facility, but then you can change it out and it can become a venue for smaller events that need something rather large space, but not quite football field sized, right? You can see that the roof is a set of basically three-dimensional space frame or basically trusses that move in two directions, right? So it's spanning this way as well as the other way. So you can see here that even there's a sort of what I would call, it kind of serves kind of like a truss, right? But the sort of facade, you can see this sort of braced structure along the sides, right? So it's an interesting sort of structural logic that they developed. You can see on the inside, then on the underneath, they use this sort of inflated FTP sort of material, I think, for the roof. And so the idea is that, you know, the Jaguars can use this as practice facility. I hope this one's good because they need all the practice they can get because they're not very good. Sorry if you're a Jacksonville fan, but they suck. Anyway, and so here was the sort of idea, the renderings, you know. And here was the Grasshopper model. Sorry, this is a little pixelated on my screen. I don't know if it looks that way on yours, but sort of, again, there's an exploded axon sort of showing the, you know, the overall idea and all the pieces, right? And so you can see the sort of structure holding up the roof. Then you can see, you know, the roof structure itself, right? You can see as a sort of two-way a truss system, right? Here they were sort of developing this, and again, this idea that the roof is actually kind of pleated, and so you get those structural folds. Right, you can start to see the geometry. They set up a big piece of geometry, then it's about how to find the isoparms along the surface in both directions. That becomes a sort of governing geometry in order to create these sort of trusses, and each one again is different. And you can see that, so you're taking a large shape, you're breaking it up into trusses or architectural or engineering components, right? And then taking each of those and doing the analysis to make sure everything works, right? And then from there they get detailed, right? And so you take something from, let's say, Grasshopper that the architect is developing, you take it into Pro Engineer or CATIA or SolidWorks or whatever the engineers are using, right? And then that gets taken out into Tesla or Tekla or some other sort of software that the steel industry uses in order to sort of develop literally every single plate and bolt and nut, right? And so every single detail is designed and engineered, right? Every single thing that's welded, right? Every bolt, again, every piece of hardware. And so here's the digital version. And not too shabby. It's actually pretty close, right? Here's the physical reality. Right? Here's how it started, how it's going, right? You know, those memes, right? So, and again, you can sort of see this, you know, it's not a typical column structure, but again, they have this, these sort of, I guess you might say, I guess you could call them columns. They're just not a sort of column grid, right? Coming to a point, right? These sort of, you know, on one side versus the other, and this sort of long span in between, right? You can see that roof. It's a great photograph if you're into trusses, right? All right. And so, you know, again, when we're talking about space frames, this is an example I saw Arup, you know, it's a huge structural, or sorry, huge engineering firm. They have structural engineering. They're not just structural engineering. They're an engineering and design firm. With, again, they're one of the largest in the universe. But you can start to see, oftentimes, this is one way to do a space frame, right? Is you have these ball joints, because the nodes are receiving lots of different struts or members from a number of different angles, right? And so, yeah, they were actually using Grasshopper to do these sort of interesting studies with that. All right, so I'm just going to quickly stop there. I don't want to bore you to death, but from time to time, we'll take a look at the sort of practical application of the stuff we're using and start to look at architectural and engineering examples of those, right? And so just wanted to sort of throw that at you. Okie doke. So let's do just a quick review of some of the basics that you guys worked on in Rhino and Grasshopper this time around. And then this time, instead of just doing the truss stuff, I'll probably do some of that, but not to just to rehash everything that's fresh in your mind. Maybe I'll back up and I'll show you, and we'll build up some of those Lewitt wall drawings, but in Grasshopper, right? And so again, we'll be dealing with points, lines, and curves, which is what you guys were dealing with as ingredients while you guys were working and building your trusses, right? But, I just want to sort of bring this full circle, and then we'll stop talking about conceptual art and Lewitt. It's not like I'm that into art, but I think it's very handy because it's, you know, again, it's a very simple. Okay, sorry, just let me bring up Grasshopper. So I already have a couple of graphs that I've made of some of these wall drawings, and again, just sort of walk you through what these look like and how they work. And as soon as Grasshopper starts up, anytime now. Windows is just doing something here. I'm not sure what. I don't know, it's weird. It didn't lag when I first opened this up. So I suspect it's loading Windows updates, and it'll ask me if I want to restart my machine, and I'll have to tell it no. I'm in the middle of a demonstration in front of lots of people, but come on now. It's another one of those moments where I opened all of these up before and everything worked nicely. I opened it up now, suddenly it's lagging pretty hard here. I haven't even opened up a file, so I don't know what's going on. Well, I'll tell you what, I'll open up that presentation really quickly, and we'll go through a couple more and some of the things that are available to you, you know, while, you know, with some of these tools. And so we'll be dealing with some of this stuff, but we can't deal with all of it, unfortunately, because this is such a crash course. But we'll be doing a lot of analysis, or we'll try to do some analysis stuff in the project too. In which case you can begin to, you know, use other softwares or other plugins with in this case, Rhino and Grasshopper, in order to do, let's say, daylighting studies, solar radiation studies, visual access studies, right? I'll just sort of quickly go through here, right? You can begin to sort of see, you know, again, how these things can start to move, and based off of those sort of performance criteria, you can start to read, let's say, how much floor area you have. You can start to compare with program, or you can begin to, again, start to look at performance criteria of some other way. You could also do form finding. So Grasshopper with a couple of plugins called Kangaroo will let you build in a physics engine. I refer back to, I don't know if you guys have heard of Anton Gaudí in Barcelona, or have been to Barcelona and seen the Sagrada Familia, this beautiful cathedral that's actually still under construction to this day. But it's famous for these sort of hanging chain models, looking at parabolic curves, right? These and approximating them by using gravity. So this is like basically a structural model of the cathedral hung upside down to use gravity. So then you would freeze these with plaster and then turn them up right side up to get this sort of geometry that's needed to withstand the gravity loads, right? Sort of catenary curves. But what's interesting is that you can do similar analysis now computationally, let's say with Kangaroo and Grasshopper, where you can begin to, this is called relaxing a surface and making a minimal surface, right? Sort of finding a, if each of these mesh edges become a spring, then you find the sort of equilibrium or the homeostasis of the system, right, as it goes. And so you can begin to see, right, this thing starts to, as you move things, right, you can start to apply things like gravity. You can start to make soft bodies and springs and other sorts of mechanical systems, right, and then watch in real time as this thing starts to find an equilibrium again. Again, I think here's another example, right, where here's a form finding where we start to generate sort of catenary vault, right? So not just an arch, but an actual three-dimensional vault, right? Using gravity and springs. We're again going through a relaxation routine where this thing will start to spring and find a sort of minimal tensile state. So here, you can sort of almost do the, like you're bouncing on a trampoline sort of thing, right? All of these become springs, just like on a trampoline. And suddenly it sort of springs back and finds that sort of equilibrium between the external forces and the internal forces, right? You can, again, this is an idea of taking something flat, then doing paper folding, right? And so again, building in those sort of dynamic systems is something else that we'll only scratch the surface of this semester, but something that can be very handy, right? Or testing something and generating solutions to complex with a bunch of sort of competing concerns. So this one is using an evolutionary solver to try to find the perfect shape for a building based off of the views this way, that way, and the other way. And again, sometimes the results are dumb and sometimes the results are pretty interesting and things that you might not have thought of as the human, right? So again, just sort of trying to understand, what's more fit and less fit as a sort of solution space, right? Based off of the parameters and criteria that you give it, right? Okay, so anyway, hopefully Windows is starting back up now, but I thought maybe I'd show you a little more what I call sort of digital architecture bling. All right, can you guys see Rhino and Grasshopper now? I hope. All right, so I'm gonna go ahead and open, and I'll just go ahead and open up. All right, so this first one is wall drawing 797. And I'm just going to turn off this grid so you can get rid of all the visual distractions here on the screen, hopefully. You can see it's basically that one where you take the first draftsman or draftsperson draws a non-straight line across the top, and then each one offsets from each one, right? So what you can see here is that I generate a set of points along the top here. Then I make a sort of random jitter, right, function that takes each point and sort of randomly sort of jitters it up and down. And then I reconnect and make a sort of non-straight line from each of those as vertices, right? Then I take that line and we basically just offset it a certain number of times, right? All right, so let me just build it up from scratch here. Let's see. Yeah, you can see I have a random number generator. And so I'm building up a list of numbers with a minimum and maximum, generating a set of random numbers and plugging them in for X, Y coordinates, right? I get a string of points. I'll turn the points on. You can see, right? I use those as vertices in order to create just a sort of nice wavy curve, right? And that curve gets offset, right? So this thing goes from left to right. Okay. Then what I do up here is I just make a rectangle, and I use that rectangle and I use it just to trim out the excess, right? So you can see that before I trim, I can turn this preview on. You can see that I have, those offsets start to move outwards, right? So if I just want to trim it because I have a wall here, right? Then I do this, I make a rectangle, right? And I use the rectangle to trim out all of these curves. So I get just the green. I'm hearing somebody's sound, so if you don't mind muting yourself, that would be great. All right, I'm not hearing anymore, thank you. All right. Here's wall drawing 138. Again, I'll just build this up step by step, but you can see that these are arcs and circles from the midpoints of four sides, right? So I find basically, here's the wall. I find the midpoint, the midpoint, the midpoint, the midpoint, right? And then from those, I start to build out a set of circles and arcs, right? All right, so how do I make that? I'll just build this up from scratch. First of all, I have 0 and 10 as numbers, right? And so I plug in 0 and 0 for the X and Y, and I make a point. Right? I'm just going to turn each of these off really quickly. Just build this up step by step. Just turn off the preview each time. Let's see. Preview selected off. There we go. So I have a point at the 0, 0, 0 point, and I have a point at the 0, 10, 0 point. So I turn that on and see, there it is. 0, 10, 0. 10, 10, 0, right out here. And then 10, 0, 10, or 10, 0, 0, sorry. Right, so I'm just plugging in some numbers for the XYZ coordinates for 4 points and just basically making the corners of a square, right? So that's 10 units by 10 units. Then I plug these in as vertices for a polyline, right? That gets closed. So for, here's the 4 vertices, right? And then is it closed, true or false? I put true, so close it up. Right. Interestingly, I can explode that, so I just get the 4 different sides, right? So I explode that 4-sided polygon, and I get 4 curves or 4 lines, right, each side. Okay. There they are. Just going to turn these off now. So step by step, I'm just sort of building this up. Preview selected off. There we are. Okay. Then for each of those sides, I find its midpoint, right? And so that's one of the things you guys did is you, in the truss exercises, you evaluated a curve at a t parameter, right? So essentially, right, you take a curve, or a line in this case, and you tell Grasshopper that I want the start point of that line to be 0, and you want the end point of that line to be 1, and then I'm going to give it some sort of address between 0 and 1, and wherever that address is falls between that 0 and 1 on that curve, go ahead and give me a point, right? And give me some of the properties of that curve. Not only do I get a point, but I also get a tangent and some other properties of the curve at that point, right? And so at this point, right, I can go ahead and change that, right? This is like, if this is Tropicana Avenue, right? This is like these X right here is like my car driving down Tropicana Avenue. As I go by, all of these street addresses, start to step upwards, right? Okay. As I move from, let's say, west to east or the other way. All right, so I'm just going to go ahead and type in 0.5 to get that midpoint. It's just like snapping to a midpoint if you're doing this. All right. Now with each of these, I need to pull out the first, second, third, and fourth. So here's what I'm doing. For each of these, I'm just pulling out these points. I'm going to draw circles from each of these. There we are. Right. So there's a circle at this point. Now, what's interesting is I plug in not just one radius, right? But I'm plugging in 110 values, right? So what did I do? I have a series widget here, right? That's another thing you guys did over the weekend, right? You just made a list of numbers, an ordered list of numbers, right? So with a series, the way I make a list of numbers is I give it the first number, in this case 0. I tell it the step size for each successive number, and I tell how many steps to perform, right? So in this case, I'm going to have 110 numbers, 0.616 units apart, starting at 0. So 0, and then 0.616, and then 1.232, and then 1.848, all the way 110 times till I get to 66.144. So what I did is I generated 110 values for the radius of a circle. And when I plug in a list of radii for a circle, then Grasshopper says, oh, you want more than one circle. You plugged in 110 values, so I'm going to give you 110 circles, and each one's going to be one of those radius values, right? So here's 110 circles radiating outwards from that midpoint. And here's the next set, and here's the next set, right? So here's the other point. There's one more point, right? All right. And all this does is it takes the original rectangle that we drew, right, and trims out all of these and just takes what's inside. Right, so here I'll turn the preview on for those, turn the preview off here, trims everything out So it's nice and neat, just along this sort of 10 by 10 wall that we started with. Yeah. So here's the adjustments for the size and the size of radius for each circle step, right? And therefore the density. And then the number of circles, is something that, we just want to make sure that we're covering the entire wall. Then of course we could change, interestingly, where those circles are drawn from, right? So we can make the points coincide with the corners rather than the midpoints, or we can move them around, right? And you start to get this sort of really interesting sort of dynamic pattern that really plays some tricks with your eyeballs especially if you're squinting at the screen like I am. All right. So again, even with something as simple as this sort of recipe that Lewitt did with the wall drawing, right, you can begin to see that there's some parametric variation that you can start to do by changing up an ingredient or a parameter, right? So we'll go with something similar. This is 130. Again, just looking at this step by step, what I do, I created another rectangle, right, from 4 points. Just turn the preview on. There's that sort of square, okay, basically. In this case, I took, I believe, each corner or each vertex for the square as the sort of center point, again, for a set of these, right? All right, and then trim them out. So again, I don't necessarily need you to know where each of these little tools are, but just sort of, again, thinking about the recipe and then step by step how we would do it. Okay, so in this case, what am I doing? I'm making a sort of random populating a region with a random set of points, right? So what this does is, what I do is let's just look at this sort of populate a two-dimensional region with points, right? Widget. So I sort of get a sense that we know what it does, right? Sort of it gives you a set of points, but here are the ingredients that it needs in order to do that. So it needs a rectangle to sort of define the region, right? That's going to place a bunch of points inside of and won't go outside of, right? So in this case, I gave it a width and a height of 18, right? Starting at the 0 point and going up and out 18 units each. Then it needs the number of values to create. And then there's a random seed engine. And so I can actually change both the random seed, right, and sort of get a different set of random points. I can also change the number of points I'm generating. So, all right. Then I'm taking each point in this cloud and drawing a line to every other point in the cloud, right? So this is the wall drawing 118, where it's, make a set of points at random along the wall, evenly distributed, and then connect each point up with every other point, right? And so I reference each of these points with every other point, and then make the connections with a set of lines. Right. All right. What's interesting is I did a variation with this, where instead of connecting with lines, I drew inspiration from some of those flight path diagrams that you see, where they're basically drawing round flight paths, geodesic flight paths around a curved Earth, but flattening them out onto a map. And so what you get is a bunch of arcs, right? So I did the exact same thing, but this time connecting them up with arcs, right? And so I thought it was kind of just an interesting little fun variation. Again, once you have a set of wall drawings, right, you can begin to sort of alter the ingredients and start to do fun things with them, right? Let's see, one more maybe before we move on from this. All right, let's go with maybe 86. Oh, okay, so this I think was something like 10,000 lines, straight lines, about 10 inches long, evenly distributed across a wall, right? And so here's what I did. I believe I'm making a set of random numbers, right? So here's a random number generator. Again, here's the domain. In other words, a minimum maximum that the set of random numbers needs to fall within. Then the number of random numbers I intend to create. And then a random engine seed number that I can always change, right? So I can always change these and do whatever with them. Then I even jitter and randomly shuffle each of the values that comes out, just trying to really create some randomness here. Although it looks like there's a repetition here that I would need to sort of fix. Let's see, then there's another set of random numbers, and then I connect these things up. So here I have random vectors. Oh, okay, so I'm generating a list of random numbers for X and Y coordinates, for points, right? And then also for direction, right? So in other words, I'm creating a set of lines by placing some points and then some random directions. Yeah, there we go, right? And so, it's not so hard to make a couple of random lines, but then when you have to make 10,000 of them or however many of them I'm making here, I guess I could do something, closer to, let's say 5,000. Oops, just move this up, 5,000, right? That's a significant time saving to, right, to generate 5,000 instantly, right? And it gives you a nice texture, if that's what you're interested in. This course is a visual art, so not necessarily architecture, right? So again, I just thought I would go through those with you guys. It was something that we talked about last week. And again, step by step, right? It comes down to usually defining those ingredients, thinking about those parameters, right? So the ingredients might be a point, it might be some numbers, right? Thinking about then the steps, right? Do I need to make these? Do I need to rotate these? Do I need to draw a line between this and this, right? If I need to rotate, right? Thinking about those parameters. What's the angle of rotation, right? Or how many copies do I make, or how many times do I repeat, right? And then basically going from point A to point B. And if you can actually, if you think about these wall drawings, the reason I like these is because the instructions are so easy. They're written out in just plain English. They're so easy to understand if they're just listed out, almost like, explain it to me as if I'm a 5-year-old making cookies for the first time, right? And that's exactly what I think we aim to do. Every time we do stuff in Grasshopper, we start off by just simply trying to think through the step-by-step instructions, and we can just quickly sketch them, diagram them out, or even write them out just in plain English, right? Just if you understand that, the Grasshopper part is is actually the easy part, right? It's sort of the esoteric part, right, that I'll help you with, right? But conceptually, if you can understand, how to create that algorithm and how to get from point A to point B geometrically, right? Thinking about those steps, that's the important part, and that's really that's really key here. And it's something that you don't necessarily need to know all of the ins and outs of Grasshopper to do, to think parametrically. That's the goal. The stuff I want you to grasp at the beginning of each of these projects, right? The technical stuff we'll get to as we go along, right? And I'm there to help you every step of the way. But you are expected to begin to think parametrically, and then to begin to create and bring your own sort of ideas to making your own recipes that can generate some of these interesting results. Okay. And again, we're talking about architectural results. So we're talking about trusses and lattices this time around, and then we'll talk about grid shells and parametric envelope systems and shading systems in the next set, and et cetera. Okay, so just wanted to sort of make that clear. All right, go ahead and close that out. So once again, I think what's interesting is going back through. Is this going to be okay? Yeah, sorry. I'm just going to quickly make a set of curves, and we'll just talk about a little bit about the geometry here, right? But if I want to make a point, right, I can of course click and snap someplace along this in this Cartesian coordinate space, make a point. But what I always do, again, you've been doing parametric design, you just didn't realize it. Every time you hit a tool in Rhino or any of your other software, right, it asks you for the ingredients it needs and some of the parameters that it needs, right? So in this case, the location of the point object, I can type in 0, 0, 0. I can give it an X, a Y, and a Z coordinate, right? And it's going to give me a point right here at the 0, 0, 0 point, right? Okay. Again, I can go around and start a polyline. I can click, and I can turn on my ortho even, and start to make 90-degree angles and start to draw, let's say, some sort of walls, right? Try to make things align, close them up. Right? or I can literally, again, start to type in explicit explicit coordinates, for each of these points, right? So the next point, right, out here. The next point out there, and on and on and on, right? Okay. So let's talk about this just a little bit. Okay. What's interesting about Rhino is that it's basically doing a lot of math with quadratic equations underneath the hood for you, right? And so what's interesting about this sort of freeform spline that I drew, right, okay, is that I can rebuild it, and I can change its parameters by saying rebuild. Oh, no, that's surface, sorry. Curve tools, there we are. I can rebuild a curve, right? And I think what you can begin to understand is that I can change its degree of curvature and basically turn it into a segmented polyline, right? And so lines and curves are the exact same thing. They fall within the exact same design space. A line is just a curve, and the curvature parameter is turned down to 0, right? And so if you begin to think mathematically in terms of the geometry you're dealing with, planes are just curved surfaces with 0 curvature. Lines are just curves with 0 curvature, right? Then I hope you can begin to sort of understand the sort of parametric space of these lines and curves. So if I go back and forth, I'll just bring up Grasshopper, and I'll turn off these other. Yeah, I'll just start a new file here. Maybe file new. I don't know what's going on here. What did I do? Oh, it wants me to open up. Okay, sorry. File new. All right. I can go back and forth between Rhino and Grasshopper. Okay. So one of the things I'm usually doing is I have, let's say, the edge of a truss or the edge of a wall, where, the edge where a wall meets a ceiling or something like, or a roof or something like that, right? Let's say something in Rhino. I need to bring it into Grasshopper so I can begin to do things parametrically inside of it. So what I do is in Grasshopper, I go to the geometry, the parameters tab, geometry, and I pull out one of these pieces of generic sort of placeholder widgets, in this case curve. And I can right click and I can say set one curve. Grasshopper disappears, asking me to select one curve or one line or edge inside of Rhino, right? So I'll do that now that that's referenced inside of Grasshopper. Now I can start to build off of this curve inside of my graph in Grasshopper, right? Okay, so if I look at these tabs, I have params, I have math, I have sets, right? Sets let me do things with lists and with numbers. Vectors let me do things with points and vectors and planes. Then I have a whole tab dedicated to curves. I have a whole tab dedicated to surfaces and then meshes and etc. And then lots of transform tools. Okay, so if I go to curve, again, some things that we did is we divided a curve, right? We evaluated a curve at a t parameter. There were several different times where we actually created lines or curves, right? So we created a line between 2 points. We created a line from a start point direction and a length. There's 2 different ways. Those are 2 different distinct ways to create lines based off of what ingredients you have, right? We also made an interpolated curve, right, for that sort of bow at the top of our truss, right? All right, so again, I can go ahead and divide this curve a certain number of times. By default, I think n is set to 10, right? At each of those division knots, I get a point, right? So when I split a curve into 10 divisions, right, 10 segments, I get 11 points out, right? Everybody notice that? I'm starting to hear somebody's microphone. So if you don't mind, since this is being recorded to post on for the class. So I get 11 points, right? All right, and if I select the widget, right, the widget turns green, and then the resulting geometry that the widget is giving me also turns green in the preview on my Rhino native modeling space. All right, so there's dividing. We did that before. We can also take a curve, and again, I'm going to right click and say parameterize the curve. what that does, that normalizes the curve. So if it takes the curve and it says, okay, the start point of the curve is 0, the end point of the curve is 1, right? Regardless of the length. You didn't know this, but Rhino actually remembers where you started clicking when you made a line or curve and where you stopped, right? And remembers the start and the end for you, right? And as a result, Grasshopper uses that stuff. All right, and so here's where I can actually plug in a number, let's say between 0 and 1 now, right? I can begin to make a point anywhere along that curve. Let's say at the end, one end would be 0, at the other end would be 1, halfway would be 0.5, a quarter of the way would be 0.25, right? All right. All right. A couple of other tools I use for some of those wall drawings, right? If I go to the vectors tab and I go to grid, there's a number of different ways to sort of populate an area with points, and grids, sort of an ordered grid, a structured grid is one of the easiest ways to do it. So there's a square grid, triangular grid, rectangular grid, radial grid, hexagonal grid, etc. Right? I can populate a two-dimensional area, right? In this case, with 100 points, there's a seed engine of 1. The region by default was set to width of width of 20, height of 10. Maybe I'll just do 20 and 20 each. Then it's rectangle, right? So in this case, what I'm going to do is I'm going to see if I can. Oh, that's weird. I don't see the actual. Oh, sorry. If I go into here, right, it's saying, okay, 0 to 10, 0 to 20. Interesting. I'll hit OK. There we go. Make that a square. Right. More about that later because we'll use this later on, but no, not so worried about it right now. So I have a point over here that I modeled in Rhino. And let me just bring that in to Grasshopper. So I'll go to my params tab. I'm just going to delete some of these extra widgets that I have on here, right? These nodes. I'm just going to right click on that point and say set one point and go ahead and select that point that I modeled in Rhino, right? Now let's say I want to make a line between this point and every point in this cloud, right? So if I just did 1 point and 1 point, I'd get one line out, right? That connects between the start and the end. But now, because I'm giving it a point here and then 100 points here, right, I'm going to get 100 lines out. There we are, right? So it's drawing a line between this start point and all of these endpoints, right? So I get 100 lines out. And again, these are generated by this random number generator, random point generator. This is referencing a point in Rhino. And if I move that point around in Rhino, I'll just select it right here and move it, right? All the lines update, right? So this is referencing a point in Rhino. If I change that point in Rhino, right, then the data updates here and then it updates here, right? So it flows from left to right as I make changes, okay? So let me turn off ortho. Let's move this one more time. There we are. I'll also move it upwards. There we are, right? Okay. Now let's take a look at some of these ingredients, right? Again, I can start to build in some numbers. So here we have the number of points to add. What do? I went to the params tab, right? That first one, right? And number slider is one of those things that we'll use over and over again, number slider. I can double click on that label called slider, and it gives me the properties here. I can constrain this to integers, so just whole numbers, along with 0 and along with all the negative values of whole numbers. I can say minimum of 1, maximum of 800, right? Okay, so now I can plug this in for the number and I can start to generate just one random number or 800, depending on how many I need, and start to adjust this, right? You can see that it changes in real time. Let me get rid of this, right, as I go. Right, so I change the amount of points and the number of them, and then suddenly I get a different number of lines, right? Okay, so same with the seed. I can change the seed engine and I get a different set of random points, etc. Okay. Any questions? I mean, I hope this makes sense as you start to do it. And we're sort of backing into it several different ways here. But this idea that, let me just pull some of these example files up that you downloaded. Let me see here. I don't think I have them, probably somewhere like over here. There we go, boxes, sets of numbers, data matching. Let's talk just a moment about the data matching stuff, okay? Let me think about this for just a moment. Let's see what we have here, points. Right, so here we made a grid of stuff, right, a grid of points. This is where sometimes it gets really sticky, but I think it's really important to sort of understand lists and data matching, because later on we'll get into something more complex where we have data trees, and you have to worry about how things match up. And we have sort of multi-dimensional lists, right? So simple lists, okay? So I just want to be very clear about what we're doing in some of these examples. I'm just going to create a new document, right? And I'm going to do the first things first. Let's not make this too complicated. What I'm going to do is make a list of numbers that's step 0, 1, 2, 3, 4, let's say 10 times, so 0 to 9 or something like that. So I'm just going to go to sequence, I'm going to go to series, right? I'm going to say the first number in the series is going to be 0. It's going to step each time 1 time, and then there's going to, it's how many steps to do? It's going to be 10, right? So that's going to give us 0 to 9, right, as a set of numbers. All I did was generate a list of numbers. There's nothing in Rhino here, right? Series just gives you a list of numbers. I'm going to use those numbers as X and Y coordinates to start to make points and plot points around my screen, just like you did with graph paper and algebra at some point, right? Probably, okay? So here's what I'm going to do. I'm going to go to the vector tab, and I'm going to use this, or pull out this widget that where I can make a point. I can construct a point from X, Y, and Z coordinates, right? All right. And so I have a list of numbers, 0, 1, 2, 3, 4, 5. What I'm going to do is I'm going to plug these in right here. Okay, for X, but not for Y. So for X, I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then for Y, I just have the same default, 0. And for Z, I have the same default, just 0. So I have 10 values plugged in for X, 0, just 1 value for Y and Z. Okay. And so what you understand is that here's what it does. Let's just pull this out so you can see it. I'm just going to use a notepad here, and I'll just plug this in so you can see the list, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Let me make another list here for the Y coordinates. See if I can plug this in. Oh, I'll just plug in one number here for 0. I'll do the same thing for Z, right? So same thing, right? I have 0, 0, and then 0 through 9, like 10 numbers here, right? So the way it matches these things up by default is it'll take the first value here and match it up with the first value here and the first value here, right? So 0, 0, 0. And lo and behold, we have a point at 0, 0, 0, right? Not a big surprise. Now, what it does is it'll try to match up the second value with this list, with the second value from this list, and the second value from this list, right? But the problem with that is there's only one value here and here, right? Okay, so what it does is when it runs out of values in the other lists, it matches the subsequent values from the other lists up with the last known value from the short lists, right? So now it's matching up 1, then 0 and 0, which is this point right here, 1, 0, 0. Now 2, it matches up with the 0 and the 0. So we get 2, 0, 0. All right, and on. So we get 9, 0, 0 over here. 0, 0, 0, 1, 0, 0, 2, 0, 0, 3, 4, 5, 6, 7, 8, 9. All we're doing is changing the X coordinate each time, right? And we're generating 10 points. Okay. Now, if we plug in a list of items, I'll just plug in this list. I'll just, delete that and make a new point here. Same way, X, Y, and Z coordinate. But in this case, I'm going to plug in this list for both X and for Y. Let's take a look. All right. And so here's how it matches up the data, right? I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 plugged in for X, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 plugged in for Y, and then 0 plugged in for Z. Okay, so the way it matches up data by default, again, to make 10 points in this case, is to take the first value and match it up with the first value, the second value match it up with the second value, third value match up with the third value, fourth value with the fourth value, and etc. Right? Now the problem is our z only has one value, so it's going to match up each of these combinations with just the last known value of z, which is 0. And so now we get 0, 0, 0, 1, 1, 0, 2, 2, 0, 3, 3, 0, right? So we can understand, right, if we had this sort of x, y, and z, right, this is 2, comma 2, comma 0. This one is 3, comma 3, comma 0 for the x, y, and z coordinates. And that's how it matches it up. Okay. Now, let's try this again. But in this case, I'm gonna plug in these for x, y, and z, right? So now you can see in the side view, they're also stepping upwards in z each time. In perspective, I think we can also see that. Right. And so again, what it's doing now is it's matching these things up 1 to 1. Again, I'll just annotate this. The first value with the first value with the first value, the second value with the second value with the second value, the third value with the third value, on and on and on, right? And so we get 10 points, right? And it has a unique value for x, y, and z each time. All right. So how do I generate a grid? I thought you'd never ask. All right, let's just take a look. Let's forget about the z for a moment. All right. Here we go. Here's my x, y, and z. Ready for x, y, and z. Here's my list of 10 numbers, 0, starting at 0, stepping up 1 each time, 10 times. So 0 to 9. The whole number is between 0 to 9. All right, so I can set a different way for it to match up the data. Okay. And in this case, what I'm going to do is I'm going to go to sets. I'm going to go to the list. I'm going to find cross-reference. Okay. And what this is going to do is it's going to list a cross-reference each of these numbers from this list with each of the numbers that I plug in for B. Okay, and so what it does in theory, right? Let's just visualize this before we look at the outputs. All right, okay. So the same thing we have plugged in for A and B, right? What it does is it cross-references the first item to the first item in B, right? The first item in A with the first item in B. And then it also matches the first item with the first item in A with the second item of B, and the first item of A with the third item of B. Okay, so it matches each item here with each item here in a serial way, right? So this one matches up 10 times, and then it moves on and matches up the second item in A with the first item in B, and then the second item in B, and the third item in B, and the fourth item in B, right? Okay, and so what happens is you get each item here matched up with each item here in some way, shape, or form. Now let's take a look at the output from these. Let's just think about that for a moment. Now I'm going to plug in the results of the cross-reference widgets for A and for B. Okay, so here we get A repeated over and over again, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times because we have 10 items in B. And then here we have the first item in B repeated 10 times, and the second item in B repeated 10 times, and the third item in B repeated 10 times. So what happens is when I plug this in, right, I get 0 matched up with 0, 0 matched up, 1 matched up with 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, all the way to 9, 0. Then 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, right? All the way to 9, 1, then 0, 2, 1, 2, 3, 4. And it does this because it cross-references all of these, right? We should have 100 values in each of these. And so what it's going to do is it's going to give us a grid of points, right? And that's what it does. Okay, so, and if I wanted to do this in a crazy three-dimensional way, I could zoom in on this cross-reference widget. I can add a C. I could cross-reference A, B, and C together and plug in C for Z. And now I have a cubic cross-reference instead of just a square cross-reference. All right, so some of you might be thoroughly confused If so, you have my apologies, but I just wanted to make sure that we're all sort of on the same page here. And don't worry if the cross-referencing, some of it makes sense and some of it doesn't, right? It comes with practice. You'll start to understand it implicitly in your head as you start to apply it here, there, and it's not like we're going to just only use this in project 1. That we're building up the fundamentals because we'll use them in projects 2 and 3, and then you'll use them all the time. Okay. All right. So with that, I think I'm going to go ahead and stop sharing. I'm going to stop recording.